I've enjoyed my time in Ecuador very much. It's sort of a cultural exchange. And so I'm going to bring a little bit of Texas to you by teaching you how to speak Texan. Okay, so we're going to practice speaking Texan. So in Texas, you say, howdy, y'all. And so on the count of 3, I want you to say, howdy, y'all. So 1, 2, 3, howdy, y'all. Very good. Now, what was it that you said? Howdy is how do you do, crunched together. And in English, there's no plural form of you. There's singular you and plural you, but Texans want to have a plural form of you, so they say y'all, you all. So when you say howdy, y'all, you're saying how do you do, everybody, or you all. So now you know some Texan. Now, as a professor, I have the right to give you an exam. And we're going to start with an exam. What industry has the largest fermentation capacity? Is it pharmaceuticals, wine, beer, or wastewater treatment? Any ideas? Well, no, it's wastewater treatment. The beer has to go someplace, right? You have to process it someplace. Okay, what industry uses a mixed culture fermentation, meaning many organisms working together? Pharmaceuticals, wine, beer, or wastewater? Wastewater, very good. Would you employ a monoculture to treat waste culture, meaning a single organism? No. Should farmers employ monocropping, meaning they grow only one crop? No. That's not good. And should you invest all your life savings in a single stock? That doesn't sound like a good idea, right? So the conclusion from this test is that diversity is a good thing. So what I'm going to do is start by teaching you about how crude oil is processed into refined products. The cost of crude oil currently is about $113 per barrel, and refined products are about $127 per barrel. And the difference in price is the crack spread, which is only about $14 per barrel. Now, if we have biomass at $60 a ton, on an energy basis, that's equivalent to oil at $20 a barrel, and the refined products would, of course, have the same value. So now we have a crack spread of about $107. So there's an opportunity to make money here if you can figure out what process goes into that circle. So I'm going to give you a mini course on biofuels. There are 4 different feedstocks that people consider, and there are a number of liquid fuels that can be produced. And always you have to go through an intermediate. It's impossible to go directly from the biomass to the liquid fuel in a single step. And we have some processes that are chemical in nature and some that are biological in nature. So let's start something that could be done in Ecuador. We would extract the oil from oil crops such as palm and react that with methanol to make the ester that's commonly called biodiesel. In Brazil, they take sugar cane and extract the sugar, which is fermented, to make ethanol. In the United States, we use corn to convert that to sugar and ferment that to alcohol. And we could also heat the biomass very rapidly to make a bio-oil, which is then hydrogenated and upgraded to hydrocarbon. Or we could partially burn the biomass to make synthesis gas, carbon monoxide and hydrogen, which can then be catalytically transformed into various liquid fuels. Or we can ferment carbon monoxide and hydrogen to alcohol. Believe it or not, there are microorganisms that will eat carbon monoxide and hydrogen. If you take acids and treat lignocellulose with acid, you make sugar, and the sugar can be fermented into alcohol. or we can use enzymes that transform the biomass into sugar and ferment that. Many companies are pursuing that technology. Or you can directly convert the sugar into hydrocarbons. These companies believe that they can do that. Or there are chemical routes to transform sugar into hydrocarbons. Now, the technology that we are employing is to take the lignocellulose using a mixed acid fermentation, make carboxylates, and then from there we use chemistry to make a variety of products. Now, all these various feedstocks, the only one that has enough quantity to be of interest is lignocellulose. And the two most common platforms are the thermochemical platform, where you make synthesis gas, and the sugar platform, where you transform the biomass into sugar. Our technology is a road less traveled. We are essentially the only research group in the entire world that is pursuing this technology. So what I would like to do is compare these three different possibilities using a common basis. I'm going to create something called balanced biomass, which is about 68% sugars and 32% lignin. Lignin is the glue that holds biomass together. So if we use the thermochemical route, both the sugar and the lignin are reacted with oxygen to make synthesis gas, and then we can catalytically transform that into alcohol or hydrocarbons, and here you see the theoretical yield. If we use the sugar platform, only the lignin is going to be gasified. The sugars are fermented into ethanol, and we'll try to turn the synthesis gas into alcohol and then into hydrocarbons. And here you see the theoretical yield. The carboxylate platform also gasifies the lignin to make synthesis gas, but we convert that into hydrogen. The hydrogen reacts with the carboxylates that are made from the sugars. That is transformed to alcohols and then into hydrocarbons. And here you see the theoretical yields. So if we compare these theoretical yields, you see that the thermochemical platform has lower yields, whereas the two biological routes have higher yields. And the reason that the thermochemical is lower is because you are partially burning the biomass. The sugars are burned, so you don't have as much energy available to make into liquid fuels. If we look at the catalytic step in the sugar platform, they're trying to transform synthesis gas into liquids, which is very difficult. If you try to transform synthesis gas into hydrogen, that's done in every oil refinery in the world. It's a very easy technology. That's called the shift process, and that's what we're trying to employ in our process. So if we complete our comparison, in my opinion, the thermochemical route has nothing of advantages. The sugar platform has one advantage, but the carboxylate platform has two advantages. And for this reason, I think it is worth further investigation. In fact, I have devoted my academic career to understanding and moving this technology forward. So with that as background, finally the title of my presentation. I'm going to introduce you to the Mixalco process, which is the embodiment of the carboxylate platform. And the first thing we do is take the biomass and treat it with lime. And here I have to go into a little story. Some years ago, I had the opportunity to speak in Mexico, and it was a similar situation where we had a translator translating into Spanish. But the translator was not technical, and so when I talked about treating biomass with lime, she translated as limone. And the group laughed. And I believe the proper word is cal. So I'm sure you know the proper word is cal. So we treat the biomass with cal and directly ferment the biomass into carboxylate salts. We then remove the water and transform the salts into ketones by heat. We hydrogenate the ketones to make alcohols, and then we transform the alcohols into hydrocarbon fuels. So what I'm going to do is step through this process one step at a time. The three things that affect the reactivity of biomass are shown here. The lignin content, remember the lignin is the glue that holds the biomass together. We have the acetyl content, which is located on hemicellulose. It makes it difficult for the enzymes to digest the biomass, and the physical structure. Now the lime pretreatment addresses these two. And it's a very simple process. You take your biomass, blend it with lime, have a plastic cover here, or a geomembrane. There's a gravel bed, maybe 1 meter depth. And embedded in the gravel is a PVC pipe that's perforated so that air can go up through the pile. So what we're going to do is take the liquid here, pump it onto the top of the pile so the liquid drains through the pile. We have air going up through the pile, and the combination of water, air, and lime makes the biomass digestible. So this is a photograph from Argentina. This is sugarcane bagasse in a pile, and you can see people on the top. So we're estimating that to be about 100 feet or 30 meters in height. The way they build that pile is they have an aqueous slurry of the biomass and water. The liquid drains away and the solids accumulate and build the pile. Now the important thing is to remove the lignin. What I'm showing is the lignin content on this axis and the time on this axis. In some cases, there was no air. In other cases, we did have air. And notice that we varied the temperature. So bagasse has about 24% lignin. And in just a matter of a few days, it dropped it down to about 17%. And then nothing more happens. But in the presence of air, notice that the lignin content keeps dropping and dropping and dropping. In fact, we made paper from this material. It had such a low lignin content. Now, I'd like to brag about these data. They were generated by Cesar Granda, who's an Ecuadorian student that worked with me for many, many years. And I will refer to Cesar multiple times through the presentation because he's played such an important role in my research. The other issue we must deal with is the physical structure, which requires mechanical treatment. And the classic way of doing this is with a ball mill. We have these steel balls that tumble and rotate and pound against the biomass, making it very digestible. And what I'm showing here is using enzymes to break down the biomass. All the data here is without ball milling, and all the data here is with ball milling. And we're looking at how much sugar can you make in 1 hour, 6 hours, and 72 hours. And this is the amount of enzyme being added. So if there's no ball milling, I can achieve 55% digestion. But with the ball milling, I achieve 85%. And we see that same pattern. In 6 hours, I can get to 55%, 85%, 60%, 85%. So what that shows is that the mechanical treatment greatly increases the digestibility of the biomass. What I'm showing here is on this axis, how much sugar do you get per unit of sugar that's in the biomass. And on this axis, I'm showing how much sugar do you get per unit of protein added. The enzymes are made of protein. They're very expensive. So what we want to do is have the highest yield of sugar per unit of biomass and the highest yield of sugar per unit of protein, which means you want to be in this region. Now, each of these represents various pretreatments that have been explored And the one that works the best is the combination of lime plus ball milling. So this shows how effective the combination of a chemical and mechanical treatment is. There's a problem, though. Ball milling is very expensive. Just the electricity required to run the ball mill will cost you $430 per ton of biomass. However, there's a solution. What we're going to do is shoot the biomass with a shotgun shell. And the way we do that is we put the biomass and water into a pipe, which you can see here. There's a cone at the top and a gun barrel. And then we have a shotgun shell here, which you can see in this image. And so we simply punch the biomass with the shotgun shell, and that shock disrupts the structure and makes the biomass reactive. So here I'm showing 5 different kinds of biomass. On the left is untreated material. The red is oxidative lime pretreatment, just lime and air. This is the ball milling, and then this is the shock. And so what you see is that the shock treatment does the best, better than ball milling in a 24-hour period. Now, when we go to 72 hours, you see that the ball milling is slightly better, but not dramatically better, and I certainly cannot afford to pay $400 per ton just for that little bit of improvement. These data I find are very, very exciting, and let me see if I can explain what's going on here. This is the rumen of a cow, which is the stomach, the first stomach of a cow. And what's shown on this axis is the amount of digestion, and on this axis is the amount of time. Now, in the United States, we feed cattle corn to fatten them up before we eat them. And this is how well corn does in the rumen. Notice in 24 hours, it's about 80% digested. And that's why cattle like to eat corn. It's very digestible. They can gain a lot of weight. Another thing that we feed cattle is alfalfa, which is a grass that has a high protein content. And notice that in 24 hours, it's about 55% digested, so it's very digestible. Now, if you feed cattle corn stover is every part of the corn plant, but not the grain. So it's the leaves, the stems, the husk, and the cob. If you feed corn stover, you see in 24 hours it's only about 30% digested. However, if we shock and lime treat the corn stover, notice that in the 24 hours it's about 65% digested. So it's more digestible than the alfalfa, which is very expensive, and it's almost as digestible as the corn grain, which is very expensive. So what I'm showing here is we can take a waste material, corn stover, that has a very little value, and by going through this process, make it almost as valuable as the corn grain itself. Now, yesterday I had the opportunity to go with Kathy. She and I took a helicopter ride to the hydroelectric dam. And we flew over the land in Ecuador, and I saw piles of corn stover in the cornfields. The farmers, after they took the grain, they would leave piles of corn stover, and I could see cows going there and eating the corn stover. But you can see that it's not very digestible. You're not going to fatten a cow on raw corn stover. But if you go through this treatment, it makes it almost as digestible as the corn grain. So I believe this will have a very large impact on our ability to feed people by taking waste materials and upgrading them to make it very digestible. Okay, let's talk about the fermentation. Essentially what I'm trying to do is make a giant cow. The rumen of the cow, I want to make it grande. So these are places where organic acids form. I've talked about the rumen, sewage digesters, swamps, and termite guts. Now, why does nature favor organic acids? If glucose, the sugar in the biomass, is converted to ethanol, the Gibbs free energy is about 48 kilocalories per mole. But if you transform the glucose into acetic acid or vinegar, the Gibbs energy change is 62 kilocalories per mole. So these organisms want as much energy as they can from the biomass. Now this is a little bit simplistic. In addition to acetic, propionic, and butyric acid, you can get some methane and some hydrogen. For our purposes, methane is not a desired product, so we put an inhibitor there that suppresses the methane formation. This shows the composition of the acids at 2 different temperatures. 40 degrees Celsius is the temperature of a cow, and 55 is the thermophilic condition. Notice that at 40 degrees, it's only about 41% acetic acid, but you get these higher molecular weight acids. When you go to elevated temperatures, you eliminate the higher acids and emphasize the acetic acid. So this is a very simple control variable that you can use to adjust the spectrum of acids that you get from your fermentation. So if you're trying to make acetic acid, which is a valuable chemical, you could operate at elevated temperatures. If you're trying to make fuels where these are more valuable, then you lower the temperature. So you can adjust the fermentation to give you the product spectrum that you're looking for. Next, we'll talk about the dewatering step. This is my favorite way to do the dewatering. We have the salt solution, the fermentation broth, coming into a heat exchanger. On this side of the heat exchanger, we have boiling brine water, the boiling salt water. And on this side, we have condensing steam. So what happens is we bring the salt water in here. In this example, I'm going to use 100 degrees Celsius. The pressure is 1 atmosphere. We take that steam, which has no salt, bring it to a compressor where we elevate the pressure to 1.04 atmospheres. Now the steam will condense at 101 degrees. So this side is 101 degrees, this side is 100 degrees. Heat will flow from the hotter to the colder, and when it does, the steam condenses, comes off as liquid, and that heat then boils more water, and so we generate more steam. So this energy is going around and around and around, and what drives that energy is the small amount of work that's invested in that compressor. Now, a key feature of this is you must have very good heat transfer. This is the boiling salt solution. This is the condensing steam. This is the metal wall that separates the 2 parts of the heat exchanger. When steam condenses here, you form a film of liquid water that acts as an insulator and reduces the heat transfer. Where on this surface, we applied a coating that is hydrophobic and promotes droplets to form. Much like if you wax your car, the liquid forms droplets. So notice that in this case, the heat transfer coefficient increased by a factor of 20 compared to the normal case where you have film-wise condensation. This has an enormous impact on making this process very efficient. We've actually piloted this technology. This is a water desalination facility for the city of Laredo, Texas. These are the heat exchangers right here, and up on the upper deck is the compressor, which is shown here. This machine and can process 50,000 gallons of water per day. In fact, it could do about 5 times more than that. It has much more capacity than what we used. Okay, now we have the salts. We're going to heat them to form ketones. And the chemistry is shown here. These are the salts, in this case calcium acetate, the propionate and butyrate. We heat them and to form acetone and calcium carbonate. So the calcium comes out in the form of calcium carbonate, and the organic molecules come out in the form of ketones, in this case acetone, diethyl ketone, and dipropyl ketone. If you want to achieve 99% conversion and operate at 440 degrees Celsius, this graph says it takes about 25 minutes, so this is a pretty rapid reaction. I won't go into much detail here other than to say this is the reactor where we make the transformation of the salts into the ketones, which are collected here as a liquid. Okay, now that we have liquid ketones, we're going to add hydrogen to make alcohols. And here you see the chemistry. The ketone groups, which are here, are hydrogenated to form the alcohol groups. This can be done in a liquid phase using a Raney nickel catalyst, a very simple process. And our computer models propose that we do a 3-stage hydrogenation. Finally, after we have the alcohols, we go through a process called oligomerization to make hydrocarbon fuels. This chemistry is a little bit more complicated. The first step is to split out the water, which leaves a double bond. That double bond is very reactive, and it will react with other double bonds, and it will grow or oligomerize a larger molecule. So here we joined 2 3-carbon molecules to make 1 6-carbon molecule. And if we want to, we can saturate that double bond by adding more hydrogen. So what I've done is I've taken an alcohol and made a hydrocarbon. In this case, that molecular weight would go into gasoline. This is a historic photograph. The date is January of 2010. This is the first time in my career that we made large quantities of alcohols and hydrocarbons from biomass. The biomass that we used was chicken manure, waste paper, and food scraps from the university dining hall. And so those waste materials were transformed into alcohols and hydrocarbons. By the end of 2010, we made 100 liters of hydrocarbons in the form of jet fuel and 100 liters of hydrocarbons in the form of gasoline. So this shows the composition of the hydrocarbons, the carbon number. These components here go into jet fuel, and these components go into gasoline. What are the advantages of our technology? We can use wet feedstocks, so you can go directly from the field to the factory. We can use a wide range of feedstocks, and I'm going to spend a little time on this. Here I'm showing a tree going into our process, but there are many, many other things that can go into the process. So let me talk about energy crops. In the United States, we grow corn as an energy crop. You can see the yield in dry tons per acre per year. In the United States, we measure land by acres rather than hectares. It's about 2.5 times smaller than a hectare. So let's talk about corn. We take the energy of the corn and put it into our automobile so we can drive. And I took this photograph off the internet of Bart and Philip. And the reason I like this photograph is Philip is holding an ear of corn in his hand. And you can see all that biomass in the background. That's the corn stover. And all you want is just the grain. You get a little bit of grain for all that biomass that you grow. So, if the United States says we're going to replace all of US gasoline with corn, that amount of land would have to be planted. And I don't think anybody here believes that that's a practical solution to the fuel problems. Plus, we have a moral dilemma of food versus fuel. So we can grow sorghum, which you see is much more productive than corn. And here you see Cesar Granda, so that's the second time I've mentioned Cesar, standing in front of 1 year's growth of corn stover. Now this looks very impressive, but Cesar's a midget. He's only about that tall, so no, he's my height. So this is 15 feet in height, and that's not the best that we can do at Texas A&M. The best variety will grow another 5 feet on top of that. So from March until November, it grew that amount. Or we can use a crop called energy cane, which is even more productive. This is a photograph of energy cane taken in Puerto Rico. Here you see 2 adult males next to 1 year's growth. You can see it harvested here. Now, what is energy cane? It's a cross between conventional sugar cane and wild sugar cane. Conventional sugar cane is bred to have a high concentration of sugar, where wild sugar cane just wants to grow. And so if you take the genes from both of those, you get a very productive crop that also makes sugar. So let me use this to illustrate that. This is the productivity in Puerto Rico expressed as dry tons per acre per year. Conventional sugar cane produces about 15, of which 40% is sugar and 60% is fiber. The energy cane, notice, is twice as productive, and also you get more sugar per acre. Now the concentration is lower, but the amount, the yield per acre is more. Plus, you get lots and lots more fiber or biomass. So how would you use this? You take the energy cane, extract the sugar, and sell that into the food market. And then the fiber goes to the Mixalco process, goes into the fuel market. The undigested residue provides the heat necessary to run the sugar mill. I'm going to mention a little bit about the extraction technology. Again, I will use Cesar Granda as the reference. He prepared these slides. This is conventional milling. You have 4, in this case, roller mills. They're very high pressure squeezing of the biomass. Very expensive. Another technology is called diffusion. This is a conveyor belt where you pile a couple feet of sugar cane onto the belt, and you just wash. Just wash, 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 wash. Eventually wash out all the sugars. Now, what we're proposing to do is a screw press conveyor shown here between each of the stages. You bring the cane in, the cane goes this way, and the water that washes out the sugar goes the opposite direction. This shows the number of stages. So for the case of a milling, you need 4 to 5 stages. For diffusion, you need about 18 stages, but the screw press conveyor is about 8, so it's in between. And we've measured the energy required to squeeze out the sugars. In the case of the screw press conveyor, it's the lowest energy consumption compared to the milling, which is the highest, and the diffusion, which is in the middle. Now, the way the screw press conveyor works is you have a cone with these screws located on it. This is a cylinder that's perforated on the outside, so it has lots of holes on the outside of the cylinder. And then we take the cone and put it inside the cylinder, which you see here. So here's the cone inserted in the cylinder, and again you see there's lots of holes in the cylinder. So as the biomass is going up through the cylinder, the water is coming out through the sides. Now, this is a qualitative description. On this axis, we show the number of stages going from milling to diffusion, so that's where we have more stages. The pressure is going this direction. In the mill, it's a huge amount of pressure, where the diffusion is essentially no pressure. We believe that if you go in the middle, where you have an intermediate number of stages and just a little bit of pressure, then the cost comes down to a minimum. I took the opportunity to imagine what would happen if we used energy cane in Ecuador. You grow about 70,000 hectares of conventional cane in Ecuador. If we put energy cane onto that land, what I'm estimating is how much hydrocarbons could you make from that. So these are just energy conversions going from acres to hectares, and this is the yield of bagasse from energy cane, and this is the yield of hydrocarbon fuels per energy cane. And so I'm estimating about 250 million gallons per year of hydrocarbons could be made. It so happens that's about the amount of gasoline that you use in Ecuador. And if the value of that is at $3 a gallon, would be about $750 million, which would represent about 0.5% of your gross domestic product. So simply by switching from conventional cane to energy cane on the land you already have, you would add about almost $1 billion to your gross domestic product, and you would actually have more sugar than you're currently producing from the same amount of land. So everybody wins. There's nobody taking a loss in that possibility. If we go with aquatic plants, such as water hyacinth, notice that the potential yield is much higher. And if you're unfamiliar with water hyacinth, these are some photographs. It's a beautiful plant in bloom. It floats on the surface of water. And it actually clogs waterways. Yesterday, when I took the helicopter ride to the hydroelectric plant, we saw many, many, many hectares of water hyacinth growing in the lakes. And it makes it difficult for transportation. We can also use municipal solid waste as a feedstock, as shown by this image. And every time I see this image, the following comes to mind, which is Back to the Future. Do you remember this scene where they put the garbage into the Mr. Fusion machine? Well, that's essentially what I want to do. We're also very energy efficient. What I'm showing here is the percentage of the energy content of ethanol that would have to be invested in the distillation. It's about 25%, where in our process, less than 2% of the energy content of the product has to be invested in the energy separation. We do not require genetically modified organisms, and there are many products that can be made, either from the salt of the acid or the acids themselves. Each of these arrows represents a chemical route to these products. Now, these products right here are hydrocarbons that we currently use as fuels, but there are many, many other products that can be made that have value as industrial chemicals and solvents. We can also do distributed processing. The idea is that each of these circles represents a farm. The farmer would bring the biomass to the fermenter. The fermentation broth, the salt solution, would be piped to a central facility where we convert it into ketones. Those ketones are then brought to an existing oil refinery where they are already converting natural gas into hydrogen. That hydrogen then upgrades the ketones to gasoline, which goes out through the distribution system that already exists. So the key here is that we're only transporting biomass a few kilometers. Thereafter, everything is liquid. Liquids transport very, very easily, unlike solids. An important point is we do not require the addition of enzymes. Our mixed culture of organisms make their own enzymes for free. And we do not require sterility, which has an enormous benefit to the economics of the process. So speaking of economics, I have to give this disclaimer. Basically, the company that we're working with, Terabon, says they have their own perspective on the economics. I, as an academic, have my perspective on the economics. They're two separate ideas. And to be a little clear about that, Terabon is interested in building the first plant. And I'm interested in what's called the nth plant. As this is a mature technology, what does it look like? So they're two different perspectives. So our perspective on the economics is shown here. On this axis, we have the plant capacity in tons per hour. And this axis, we have the selling price of the hydrocarbon fuel, including profit, return on investment. And each of these lines represents a different feedstock cost, ranging from negative $60 a ton, which you would get for accepting municipal solid waste as a feedstock, to as much as $120 a ton that you would pay the farmer. Now, what I've been using as my reference is $60 a ton, which is this line right here. And you see there's a shoulder, roughly 100 tons per hour. Going much larger than that doesn't buy you a whole lot, but going smaller than that is very expensive. So that's kind of a reference point where you'd like to be. And this red line here shows the capital cost of the plant in millions of dollars. Now, at that reference point, if we go to a large plant, we're estimating about $1.76 per gallon would be the selling price of the hydrocarbon fuels, which corresponds to crude oil at $63 a barrel. So as long as crude oil is more than $63 a barrel, our technology is the cheaper way to make hydrocarbon fuels. Some history on our technology. I began researching this over 20 years ago in 1991. In the year 2000, we started building a pilot plant, which is shown here. It's located on campus. And in 2008, our industrial partner, Terabon, started building a demonstration plant in the cooperation with partners Valero, which is a very large oil refining company in the United States, and Waste Management, which is the largest garbage hauler in the United States. So this is my third reference to Cesar Granda. He's the engineer that drew the first drawing of the fermenter. It's a pit lined with concrete and covered with fabric. So here is the pit being dug, and it's being lined with concrete. And these are the tanks that store the fermentation broth. There's 4 of them. And here you see the tanks next to the pit. This is a photograph of the inside of the fermenter. These are the concrete walls. All the liquid drains into the sump, and once it's collected in the sump, you simply pump it back through the biomass. And here's that fabric cover that I mentioned. And this is a photograph of the outside of the fermenter. Now, the next image is an artist concept of what the fermenter should look like, because we're trying to make a giant cow. We had a dedication ceremony where Governor Perry was there to help us celebrate, and I got to speak there as well. And these are the people that founded Terabon, Emil Ogden and David Carrabba. Here's the Holtzapple family posing with the governor. And I had the opportunity to bring the governor inside the fermenter, explaining how everything works. And here's my son, John, looking into the future. Okay, so some conclusions. There are no scientific breakthroughs required. We simply have to scale it up. The engineering is all that's required. It's commercially ready and economical. So here I show a few scenarios of interest. If we have 40 tons per hour, which is a rather small plant, and we pay the farmers $60 a ton and make our own hydrogen from the undigested residue, the gasoline would sell for about $2.56 a gallon. If we go to a very large plant, still paying the farmer $60 a ton and making our own hydrogen, the cost drops to about $1.76 per gallon. If we go back to the smaller plant and pay or get a tipping fee that people pay to get rid of garbage, and make hydrogen from methane or natural gas, the price is only $1.24 per gallon. Okay, so we have a pre-test, we have to have a post-test. Should we encourage diverse approaches to biomass conversion? And I hope you'll agree that the answer is yes. And these are the organizations that have worked with me over the years. And the question some people ask is, what's the next step? Where do we go from here? Well, Terrebonne wants to take municipal solid waste and make it into gasoline. The first plant would be roughly 200 to 300 tons per day, which is the waste from a city of about 150 to 200,000 people. And they're planning to begin construction in 2013, which is next year. Through DARPA, which is the Defense Research Agency that brought you GPS positioning and the internet, they also have funded our work. I hope that will become equally as valuable. In phase one, it was a $20 million project. The goal was to make a pilot plant scale process that produces 100 liters of jet fuel. We were successful with that, and so we moved to phase two, which is a $17 million project, which at the demonstration scale plans to make 6,000 liters of jet fuel. Our goal is to accomplish that this fall. And then next year, the plan is to go to phase three, which is to build a commercial plant. Now, during phase one, there were 21 organizations, each pursuing their own favorite biofuel technology. Remember at the beginning, I gave you all the different possibilities. In order to continue with the funding, every 3 months, you had to produce 2 liters of jet fuel. And all of those organizations were unable to meet that milestone except for the carboxylate platform. We were the only ones that successfully met the milestones and produced the 100 liters of jet fuel. So when we passed to phase two, DARPA did not want to put all of its eggs in one basket. They had 2 companies that started, but you still had to meet the milestones. Very quickly, the other company was unable to meet the milestones, and again, Terrebonne is the only one to survive. They are the only ones tasked with making the 6,000 liters of jet fuel. So this final slide is my grand vision. What I would like to do is grow crops, for example, energy cane in Ecuador. We bring those crops to the local Mixalco process where they're converted into ketones. Those ketones are then brought to a refinery that already exists, where we use hydrogen made from natural gas, which they're already doing, and use that hydrogen to upgrade the ketones to make gasoline. The gasoline goes through the existing infrastructure to be brought to your car. So this gasoline would be indistinguishable from the gasoline that you're already using in your car. When the exhaust comes out the tailpipe, it has carbon dioxide. Then through the process of photosynthesis, we fix that carbon dioxide and make more plants. So what we have now is a cycle where the carbon just goes around and around and around. Now we are using, in this example, natural gas, which does release CO2. If you don't care about global warming, you just let it go into the atmosphere. If you do care about global warming, then you take that CO2 and put it under the ground. So what I'm proposing here is a process where we can actually use abundant fossil fuel reserves and still address global warming. So in my opinion, Ecuador, Colombia, Venezuela, and Brazil in the future will be the Saudi Arabia of biofuels. That as Europe, which is already very sensitive to global warming, decides they're going to do something about this, they don't have enough land in Europe to grow the biofuels that they required. They're going to have to outsource the biofuels. If you look at land use in the world, China is trying to feed its population. India is trying to feed its population. The United States will probably be self-sufficient. We have enough food and we can grow our biofuels, but we probably won't be able to export very much. the only place in the world that has the land and the water and the climate to produce significant biofuels is Central America and South America, near the equator. You are in a wonderful position for the future. And so what I'd like to do is close, and I hope that I've stimulated some questions from you. Thank you very much for your attention.